I'm sure you all want to hear a little bit more about our discrete Xe GPU architectures. If you step back and look at what we have been doing recently, you'll see that we have made tremendous progress on integrated GPU hardware and software in less than 3 years. We have effectively doubled performance year over year, 2 years in a row now. First with Gen 9 to Gen 11, and then with Gen 11 to XeLP. This was an incredible start, and this effort removed friction for millions of users. We raised the performance bar for ultra-thin mobile devices. But as we have already announced, we have bigger plans. Integrated graphics is constrained, but discrete, on the other hand, is unconstrained. Well, relatively. This is a great time to be entering the high-performance PC graphics market. Why are we doing this? Why now? These are extremely exciting times. Game engines and software teams are producing near real-life in-game visuals in real time. And leading-edge hardware is enabling everything to come together to deliver incredible experiences that allow gamers to feel more immersed than ever before. Publishers, developers, gamers, and creators are constantly pushing the boundaries of what is possible, always asking more from their hardware, and they are also looking for more innovation and choice. The PC ecosystem is built around innovation and choice. Many different OEMs, many different shapes, sizes, and form factors, and many different operating systems, and a diversity of software. The vast choice of what to buy, or the flexibility to build your own PC, to customize, upgrade, and to modify. These are some of the reasons the PC market has been so popular and exciting since the beginning. These are the reasons the PC ecosystem is great. 1.5 billion people are PC gamers. Our focus today is to deliver a better experience for gamers and creators, to give them innovation and choice in hardware coupled with open and accessible software and tools. To create a great experience across form factors, segments, and users, to remove friction and deliver high-performance graphics experiences to everyone, we recently unveiled Arc, which is a brand for our visual computing products. The word arc is used to describe the narrative flow and the various plot inflections of a story. Every gamer, game, and creator has a story, and every story has an arc. The Arc brand represents the next chapter of our story and our commitment to removing friction from gamers. Building great GPU hardware is necessary, but nowhere sufficient. Great software plays a critical role for the user experience. To discuss the progress we are making on software and user experiences, please welcome the leader of our GPU software team, Lisa Pierce.
Thanks, Raja. With our first high-performance gaming GPU, it goes without saying that performance and quality are job one. First, at the heart of our focus is the design of the core driver itself. That covers integrated and discrete graphics products in one unified codebase. We've completed a re-architecture of these core driver components, specifically our memory manager and compiler. As a result, this year, we've improved the throughput of CPU-bound titles by up to 18%, and improved the game load times by up to 25%. This load time reduction was accomplished through enhancements to our stage compilation technology, such as eliminating redundant shader compilation and improving task scheduling for our compiler threads. We also completed a major refactor to fully optimize our local memory utilization on our discrete graphics products. At the same time, we implemented over 30 large optimizations affecting over 100 gaming workloads that rolled out in our existing install base this year with our unified graphics driver. Now, we are always about new APIs and engines, since new games are always pushing up the visual quality bar. For the last 3 years, we've been co-engineering new features for DX12 Ultimate with Microsoft. We're excited that at launch, we will support hardware-based ray tracing, mesh shading, and sampler feedback. Together, these technologies deliver next-gen visuals in games like Hitman 3, Chivalry 2, and many others. We've also been working closely with Epic, and I'm excited to tell you that Unreal Engine 5 runs on our discrete graphics GPUs today. We can't wait to see what game developers will do next in their next generation engines. At launch, we'll also enable updates to our user controls to help gamers take advantage of these technologies, including support for AI-assisted virtual cameras, game highlights, and of course, capture for streaming that will make use of our high performance and quality hardware encoders. And we also will integrate all of our overclocking and performance interfaces directly to the app. And finally, in the end, it is all about experiences. One thing that gets us really excited is enabling a range of experiences across product segments, from integrated graphics to high-performance discrete. And today I'm excited to share a new feature that will do just that. But first, some background. Given a fixed amount of performance potential in a GPU, gamers are forced to make a choice between high quality and acceptable performance. There are cases where you have content that already runs close to 60 FPS at 4K, and the frame rate can be further increased by upscaling. Or you can have a more recent content like ray tracing that needs a performance boost even to achieve playable frame rates. Over the years, games have developed various technologies to reconstruct a high-res image from fewer pixels. These technologies use novel algorithms to reconstruct details from neighboring pixels in space or time, but they're often accompanied by issues like blurring or ghosting. And these technologies can often fall short with high-quality rendering, like ray trace reflections and shadows, detailed geometry, or high-res textures. Additionally, there's computational overhead in doing these operations. Ultimately, we want to target this region of high performance and high quality. Our solution to this problem is XeSS. XeSS is an easy-to-integrate API, and it fits within today's game engine flow. It uses deep learning to synthesize images that are very close to the quality of native high-res rendering. It works by reconstructing sub-pixel details from neighboring pixels, as well as motion-compensated previous frames. This reconstruction is performed by a neural network trained to deliver high performance and great quality. Now let's see XeSS in action. This is a demo prepared by Rens using Unreal Engine. We can see the demo rendering real-time in 4K, but in reality, the engine renders to a smaller 1080p render target, which is upscaled to 4K by XeSS. Compared to rendering in native 4K, there's no visible quality loss. Upscaling from 1080p to 4K with XeSS gives the same quality image as rendered in native 4K. In this scene to the right, you can see the actual content rendered by the engine. The left side shows how this 1080p image is upscaled by XeSS to achieve the final high-quality result. Rendering to a smaller 1080p render target allows to significantly reduce the rendering time and achieve higher frame rates. The cost of upscaling operation remains relatively small compared to the overall render time. Thanks to the use of AI-assisted scaling, we can also achieve up to 2x performance boost. And now, games that would only be playable in low-quality settings can run smoothly at 4K. It may be a challenge to see these details in the live stream, so we've added a high-resolution video in the demo area that can be viewed on demand. Our goal with XeSS was to deliver neural network-based supersampling for a wide range of GPU hardware across the industry. The demo you just saw was running on our recently announced Arc Alchemist SoC, leveraging our new XMX hardware acceleration that we'll discuss further in a few minutes. In addition, we also came up with another innovation to enable XeSS on a broad set of hardware, including our competition, with a smart quality performance trade-off. We accomplished this by using DP4a instruction, which is available on a wide range of shipping hardware, including integrated graphics. This brings the benefits of XeSS neural supersampling approach to millions of gamers. I'm thrilled that everyone can experience XeSS. We're excited to have several early game developers engaged on XeSS. The SDK for the initial XMX version will be available for ISVs this month, and the DP4a version will be available later this year. At Intel, we believe in open source standards. XeSS APIs will mature as we gain broad support for games and hardware, and we will open up the tools and SDKs for everyone. To learn more about XMX and our Xe HPG GPU microarchitecture, let me bring in our GPU Chief Architect, David Blythe.
Thanks, Lisa. Hi, everyone. It's time for our new GPU microarchitecture to be introduced to the world. This microarchitecture, which we call XeHPG for high-performance gaming, is the convergence of our XeLP, HP, and HPC microarchitectures. XeHPG is engineered to deliver great scalability and compute efficiency with advanced graphics features. Today, I'll give you a brief introduction to the new compute, graphics, and scalability capabilities of XeHPG. To deliver scalability beyond XeLP in XeMax and build enthusiast-class hardware, we've had to rework the fundamental architecture of our GPU. Starting with the heart of the engine, we defined a new compute building block, which serves as a foundation for the Xe architecture. As part of this architecture change, we're also taking the opportunity to update some of the naming, so you won't hear us talking about execution units or EUs much anymore. The execution units are getting too large to reason about, and the generational changes make it difficult to do comparisons. So allow me to introduce the Xe core. Xe cores include efficient arithmetic units, caches, and load store logic. The arithmetic units include engines for traditional floating point and integer vector operations, along with engines to accelerate convolution and matrix operations commonly found in AI workloads. The architecture gives us a core ISA with the flexibility to adapt the Xe cores for specific workloads and market segments. I don't have time to tell you everything about the Xe cores we've built for our XeHPG microarchitecture today, but I can share some details. For XeHPG, Xe cores include 16 vector engines and 16 matrix engines, which we refer to as XMX or Xe matrix extensions. And you've already seen XMX in action with the XeSS demo presented by Lisa. With more and more workloads infused with AI, XMX is a key engine for delivering more efficient compute. The XeHPG microarchitecture is designed to be gaming first and to build much larger GPUs compared to the maximum of 6 Xe cores in XeLP. We scale the hardware required for real-time rendering in a larger building block we call our render slice. The render slice contains 4 Xe cores and the rendering fix function for real-time 3D graphics. The rendering fix function includes geometry, rasterization, samplers, and pixel backends, designed for DirectX 12 Ultimate with support for variable rate shading Tier 2, mesh shading, and sampler feedback. Each slice also includes 4 new ray tracing units architected to accelerate ray traversal, bounding box intersections, and triangle intersections. They provide full support for DXR DirectX ray tracing, as well as Vulkan ray tracing.
Thanks, David. With Xe cores and their advanced feature set, we now have next-generation real-time graphics. But we also wanted to scale this to enthusiast-class performance. Can you walk us through how we achieved that?
Of course, Raja. To scale our performance to enthusiast-class GPUs, we work on 2 fronts. First, we replicate these slices, and then we connect them to a shared L2 cache through a high-bandwidth memory fabric. We have the flexibility to scale to different configurations, up to 8 slices. To hit our performance goals, not only did we create an architecture for building larger GPUs and add additional features, but we also challenged ourselves to increase the power efficiency and the operating frequency of the design. Working across architecture and engineering, we performed detailed analysis for power reduction opportunities, which resulted in new methodologies and optimizations at every level of the design, from the Xe core on up. The changes were spread across microarchitecture, logic design, and physical design, and often needed complementary changes. It was truly a team effort, and I'm delighted to say that compared to the XeLP IP in our Iris XeMax product, we increased the relative operating frequency and the performance per watt each by roughly 1.5 times. I should also point out that the team effort included close cooperation with process technology, and that too contributed to the great results. I'll hand things back to Raja, and he can elaborate on that a little bit more.
Thanks, David. Last year, I told you that XeHPG GPUs would be built with an external foundry partner. Today, I'm happy to unveil that our partner is TSMC, and Alchemist GPUs are built on the N6 process. This is the wafer of Alchemist. This is a great example of our IDM 2.0 partnerships. We have the flexibility to make the right process choice for each architecture. The progress I witness in our labs week by week with Alchemist GPUs and its software is very encouraging. Alchemist GPUs are now sampling to ISVs and partners. I can't wait to get the first generation of our products in your hands by Q1 of 2022. While our post-silicon and software teams are working very hard to get this to you, our design and architecture teams are busy creating the next few generations of our gaming GPUs. Here I have the code names: Battle Mage with Xe2, Celestial with XE3, and Druid after. Can't wait to share more at a future event, hopefully live.